Charge Tapes Lab by Drew Peljovich. Introduction. The Charge Tapes Lab experiment consisted of two pieces of tape acquiring a net positive charge by being rubbed against a third neutral tape. By creating the pieces of tape and performing experiments on them to collect data, we can calculate the net charges on them and model the tape in GlowScript using computer code. The experiment. The experiment consisted of charging pieces of Scotch tape and observing their interactions to determine the charge on one tape. The dimensions of the tape are as follows. The density was 1 gram per meter, the length was 0.02 meters, and the width was 0.019 meters. To calculate mass, simply multiply density by length to calculate that mass was 0.02 grams. To check if the tape was charged, I placed my neutrally charged hand near the tape, and since it was attracted, I knew that the tape was charged. Furthermore, when two pieces of tape were placed next to each other, they were repelled, and that indicated that they have the same charge. When the two charged tapes were placed on top of one another, the higher tape began to float when they were just 0.02 meters away. To check whether the tape was positively or negatively charged, I rubbed a plastic pen on a piece of cloth, creating a negative charge on the pen, and brought it near the tape. Since the tape was attracted to the pen, I reasoned that the tape had a positive charge because it attracted the negatively charged, opposite charged pen. To calculate the forces on the tape, I started with gravitational force. Using the equation force equals mass times gravity, and substituting the values, I got the answer that the force of gravity was equal to 0.196 newtons. To get the electrical force, I simply used the fact that according to the free body diagram, electric force and gravitational force were equal and opposite in direction, and therefore electric force was also 0.196 newtons upwards. To determine the charge on the tape, I used the fact that electric force and gravitational force are equal to say that E times Q equals M times G. Solving for Q, I was able to find that the charge on a piece of tape is 9.33 times 10 to the negative 8th coulombs. Dividing that number by the charge of a single electron, I found that the number of the electrons on a piece of tape was approximately 5.833 times 10 to the 11th electrons. However, using the measurement of the tape and the length scale of the atom, I calculated that the number of electrons was actually 200 million. The discrepancy in these values is due to imperfect measuring of the distance between the two tapes and other human measuring errors during the experiment. The computational model of the tape can be seen on this slide with its computer code shown. As you can see, the gravity scale and the electric scales are widely different in order to be able to see both vectors on the model on the next slide. The reason these scales had to be so different is because the human error in measuring made it so that the two vectors do not exactly equal each other. The 3D model of the tape is shown here on this slide. According to the computational model, the charge on the tape was equal to 9.33 times 10 to the negative 8th coulombs. And in order to make this calculation, only one assumption was made, which was to assume that each tape had the same amount of charge and that it was evenly distributed along the line of charge. For this computational model, which is in difference to the last lab that we conducted, the assumption that the tape was a point charge with all charge concentrated at the center can no longer be used. Also compared to the last lab, there are two very big differences between the electric forces calculated. When the tape was treated like a point charge, the total electrical force was calculated to be 0.1962. However, in this lab, when treating the tape like a line of charge, the electrical force was calculated to be 3.12464 times 10 to the negative 8th. The point charge is a lot larger in magnitude because all of the charge on the pieces of tape was focused in the center, with none of the charge diminishing as it got further away and the radius increased. The line of charge takes this matter into account, and so the magnitude is a lot lower because as you go farther away, the electrical force diminishes. In conclusion, the lab taught me how to calculate the charges on the piece of tape, and using observations and computer modeling to provide a rough estimate of the actual experiment on the computer. Using that same code and some equations, I was able to gather data on the tapes to determine their charges and the forces acting on each one.